Hey guys, today I'll be running through the solution of the given problem. The population of bacteria grows at a rate proportional to the number of bacteria at time t. After 3 hours, it is observed 400 bacteria are present, and after 10 hours, 2,000 bacteria are present. What was the initial number of bacteria? First off, we will go through and list our parameters given by the problem. Our population we'll call P, our time in hours we'll call T, and the population at time equals 3 hours equals 400, and our population at time equals 10 hours is equal to 2,000. These are our initial conditions, and we have our proportionality constant that the problem notifies us about. First off, we will write our first equation. It is given by the first sentence. The population of bacteria grows at a rate, dP over dt is a rate, grows at a rate proportional. Our proportionality constant is here. We notice here that this is a separable differential equation because we have dP on this side and P on this side. So we'll start off by multiplying both sides by dt. This means that this dt in the denominator will cancel. We're left with dP equals k times p times dt. Now our goal is to get the p with the dP. So we divide both sides by p. This p here cancels, and we're left with 1 over p times dP is equal to k times dt. Now we can integrate. Integral of 1 over p is ln of p, and then the integral of k dt is going to be k times t, and then plus our constant because this integral is indefinite, meaning that there are no upper and lower bounds. Now our goal here is to isolate p, so we use e as a base to get rid of the ln. So we're left with p is equal to e to the k times t times e to the c. This is because of our properties of e. When you have e to the a plus b, it is equal to e to the a times b. So see that resemblance here? Or you can write it as p equals c1 times e to the kt. I did this because e itself is just a number, and c is obviously going to be a constant that doesn't change. So when you have a number raised to another number, that's going to be a number. So instead of holding this term across the problem, we could just call it c1 and make it a lot easier. So our general solution is p equals c1 times e to the kt. In order to proceed with this problem, we must use our initial conditions given by the problem, which are population at time equals 3 hours equal to 400, and our population at time equals 10 hours is equal to 2,000. So the 400 and the 2,000 are going to be plugged into P in our general solution, and then the numbers within the parentheses, those represent our T values. So we are left with 400 is equal to C1 times E to the 3K. And equation 2 is 2,000 equals C1 times E to the 10K. Notice that we have two equations and two unknowns, meaning that we can eventually solve for C1 and K. I think the easiest way to do this is to divide equation 2 by equation 1, because as you can see, the C1 terms will cancel out nicely, and that means you're left with only one unknown, meaning that you could solve for it. So I simply divided the left side of the equation by the left side and the right side by the right side. Now we are left with 2,000 over 400 equal to 5, and C1's cancel, and we are left with e to the 10K over e to the 3K, and that becomes 7K based on properties of e. If you have e to the b over e to the a, you're left with e to the b minus a. So 10K minus 3K is 7K. Now we can solve for k pretty easily. We take the ln of both sides to cancel out the e. Left with 7K equals ln of 5. Simply divide both sides by 7, and we get our k value. This is a number, but I'll leave it in this form just for the sake of precision. Now we must plug this back into C1 to find plug this back into equation 1 to find C1. So k value gets substituted here, and we're left with 400 equals C1 times e to the 3 times what we just found. Simply divide both sides by this whole e value here, left with 400 over e to the 3 times ln of 5 all over 7. And plug this in your calculator, you'll get C1 equals 200.7. Now we could do what the problem's been asking for and find the initial population, or P at time equals 0 hours. So we have our C1, we have our K, we're ready to do this. Once again, using our general solution, we have P0 equals C1 times e to the K at time equals 0. So T is 0, meaning that e to the K times 0 will be e to the 0, which becomes 1. So that term essentially goes away completely. So we're left with P at 0 is just equal to C1, which we just found. So the initial population is equal to 200.7. Thank you guys for watching. And if this video helped you, hit that like button. I'll see you guys in the next one.